Howdy, Brian Vikings. We're here to talk about titrations. Now, titration is a controlled addition and measurement of the amount of solution of known concentration required to react completely with a measured amount of a solution of an unknown concentration. So here's my known concentration in my burette, and my unknown concentration is the thing I'm trying to measure or I'm trying to analyze. So I will call this stuff that's in the burette, I will call it the titrant. Means I have the known volume. I can measure volume by the graduations on the glassware, and I know the concentration of the solution that I put in there. Now my analyte, I know the volume that I put in this analyte, but I do not know the concentration, and that's what we're trying to find out. Now, when we do titrations, we end up mathematically getting these little curves, and I want you to try to unpack this information. On the x-axis, we have the volume of base added, and on the y-axis, we have the pH. So if I titrate a strong acid with a strong base, what I'm going to do is I'm starting with an acid. So the pH is quite low. Now, if I add base to it, it will neutralize the acid and the pH will start to creep up. It will creep up and creep up until I get to this point where I get to this inflection point right here. Now, at this inflection point is right here, this equivalence point is where the moles of acid and the moles of base equal each other. I can tell that because there's exact same number of acid and exact same amount of base because the pH is 7. Now this is with a strong acid and a strong base. The pH will be 7 at the equivalence point. After that, as I keep on adding base, my pH goes above 7 and we start getting more and more data over here. The only data that's really useful is this point right here, and this is where we're trying to get to. To separate these, you need to notice that there's a steep curve and the equivalence point is at the pH of 7. Now, if we're doing a strong base into a weak acid, so I'm adding sodium hydroxide, which is a strong base, and I'm starting with a weak acid, so the pH is a little bit higher. It's about a 3. You will notice a smoother curve, and the curve will kind of flatten out, and we will get an equivalence point higher than 7. Okay, so that's what happens with a strong base and a weak acid. Now, the weaker the acid, the higher the pH will start with, and you will also get a flatter curve. But that's just a fun little enrichment. Um, to titrate a strong acid into a weak base, we will do the same thing, even though now I'm adding a strong acid in this case, HCl, and now I'm starting with a base. So the curve will actually fall down instead of moving up. But we still get the same kind of idea with the equivalence point, and the equivalence point is now going to be less than 7. Now, a diprotic acid has 2 protons to give. So since it has 2 protons to give, it will have 2 different equivalence points. Now, for this reason, we don't usually use diprotic acids for titrations because we get 2 points and it's hard to find 2 different data points off of this. But it is possible, and this is what you would see. For a triprotic acid, you would see 3 equivalence points. Now to do this, you're going to use a burette. A burette is a long piece of glassware with many graduations on it. Now a burette's markings are backwards than what you're used to. The markings will increase as they move further down the burette. Normally you're used to seeing them decrease as they move down the burette. So it's important to look out for that. The volume is recorded before and after on that burette. So now, quick quiz. What's the reading on this burette? Well, hopefully you said 42.30. That's because it's between 42 and 43, so I know it's going to be higher than 42 but less than 43. And I notice the graduations. There are 10 lines here, so each line is worth a tenth of a millimeter. And so I go down 1, 2, 3. And now I need to estimate one more decimal place. I need to estimate one more significant figure. And that's crucial to this. So you actually get 4 sig figs off of this burette and count on that, and you'll be tested on that. Now, to perform the titration, a measured amount of acid or base of an unknown concentration is added to a flask using burette. I will then add a few drops of indicator to the analyte in the flask. The indicator will not change the pH, it's just there to change the color. So it's more of a spectator, it doesn't actually participate in the reaction. Now, the initial volume of the burette is recorded, and then the volume of base of a known concentration is added from the second burette until the indicator changes color. Now, we always swirl the analyte continuously to make sure all the contents are able to mix. Then the titration is finished when the indicator changes color and the end point is reached. The final volume of the burette is recorded. So many students will forget to measure this. They'll only go after the final volume, but it's useless unless you remember to measure the volume of the burette twice. You have to measure at the beginning and you have to measure at the end. So watch out for that. So now what we have here is the analyte, and we have our analyte again, and we were adding our titrant to it dropwise, and we will add the titrant until it changes color. Now, when it changes color, we will stop and we will note the volume of the burette. I will note it at the beginning and note it at the end. The difference between the two of them is the volume of titrant that I added, and that's going to be crucial. Now, you've heard me say an end point and an equivalence point, and they mean two different things. Now, the equivalence point is when the two solutions in a titration are present in chemically equivalent amounts. Also, an easier way to say that means that the moles of acid will equal the moles of the base. This is the most important part of a titration, is at this point. That's what we're trying to get to. Now, the endpoint is simply just where the indicator changes color. So there are many indicators to choose from, so a good chemist will choose an indicator that has an endpoint approximately the same as an expected equivalence point. There are many different indicators that you have. Here's a not very good reference chart for this, but you see different indicator colors here and color ranges, but here's a better one where we have multiple indicators written out, and you can see how they change from either yellow to blue, or yellow to red, or colorless to pink, or something like that. Now, they all have different ranges, they all change at different times, and they all have different colors. So it's important to keep those in mind. You don't have to memorize them, you don't have to learn them. Now, an important note is the universal indicator down here is actually a really lousy indicator for a titration because it gives such a wide range of colors and it's hard to tell when it actually changes. It looks really cool and it's fun to use for demonstrations, but not great for titrations. So to do the calculations, there is a lot of information you have to be able to unpack. There is an initial and a final volume of HCl. There's an initial final volume of base, okay? And then there's a concentration of HCl solution. So this is the one that I knew the concentration of, and I want to calculate the concentration of NaOH right here. Okay, so the first step is to actually find the true volumes of acid and base that I used. So I'm going to take my volume of HCl and I'm simply just going to subtract the two numbers to find my actual volume that was added. I'll take my volume of NaOH and I'll subtract the two numbers to find the volume of base that was added. On the next slide, I've condensed some of the information into the most important parts. So an acid, the acid required this much volume and this concentration. This base needed this much volume and it had an unknown concentration. Step 2 in your notes says to write out the equation. And the reason why we do this is to make sure the mole ratio is correct and make sure the coefficients are balanced. That will be important for our calculations. At the equivalence point, the moles of acid and the moles of equals the moles of base. So this means that we can use our solution stoichiometry. So I'll start with my moles of acid right here. I'll start with my volume of acid, and I just put a 1 here just as a placeholder to make sure you guys know that this is in the numerator. And then I am multiplying by my molarity, moles over liters. Well, since this was in milliliters, I went ahead and made this 1,000 milliliters. Okay, so this is moles over liters, or moles over 1,000 milliliters. This is my molarity, and this is my mole ratio. This will change my moles of acid to moles of base. The coefficients in the equation are 1 and 1, so I just use a 1-to-1 mole ratio. This will give me the number of moles of NaOH as 0.002672. I now just have to calculate my molarity as moles over liters. So it's this number of moles divided by my number of liters. That is my volume of base converted to liters. So I would move this decimal place 3 places to the left to find my number of liters. And I find out that my molarity is 0.079 molar NaOH. Your last example will have sulfuric acid and potassium hydroxide. Now, sulfuric acid is a diprotic acid and would not be preferred to do in a titration, but we can do it, and we are going to assume that both of these protonate, which means both of these hydrogens are given away, and we're just going to assume that there's only one equivalence point during this calculation. So the concentration of sulfuric acid is known, and the concentration of potassium hydroxide is unknown. So I need to find my volumes just like I did before by subtracting my two numbers and find my actual true volumes. I'll then organize my information so it's easier to read, and I have my volume and molarity of acid, my volume and unknown molarity of base, and I have my equation written out. Now, it was absolutely crucial to do it this time because the coefficients is not always a 1-to-1 mole ratio, and that's going to make a difference later. So again, the moles of acid equals the moles of base in this example, okay? So that means that I have my volume of acid, and I multiply by my molarity of acid. That's my moles divided by liters, or 1,000 milliliters. And then I use the mole ratio to convert to my moles of my base, my potassium hydroxide. Now I find that my moles of potassium hydroxide is 0.005538, and then I use my molarity equation again as moles divided by my volume of base, which is 0.0157 liters, and I get 0.35 molar KOH. Please note that this number came from up here. Okay, that's where that came from. All right, time to practice. You guys have your worksheets ready, and this should be the last one. There are multiple pages to this one, but you need to be able to identify the titration curves like I talked about in this video. Y'all have a good one.